This is the screencast for section 6.1, example 3, handling discontinuity on an initial value problem. Alright, so this may seem a little strange to you, but on a discontinuous function, whether that be a jump discontinuity, infinite, or removable, the initial value or the value that you're given will only specify the particular solution for that continuous piece of the function. So beyond any discontinuity, we need a new point that it would pass through to find out the solution over there. So for example, example 3, find the particular solution to the equation dy dx equals 2x minus secant squared x, whose graph passes through the point 0, 3. So first we multiply both sides by dx and find the differential dy. Then we're going to integrate both sides. The integral of 2x is x squared. Integral of secant squared is tangent x. The minus sign stays the same. And then of course we have our plus c that did not cancel out because it's an open integral. Then we're going to plug in the point that they give me, 0 and 3. So 0 in for x, 3 y, 3 in for y, and c equals 3. So I have my final statement. However, this graph has discontinuities. So I need to find those discontinuities, and I know those are going to lie where tangent of x equals 0. Well, tangent, or undefined, tangent is sine over cosine. So when cosine is 0, that's when tangent is undefined. So cosine is 0 at, let's see, negative pi over 2, 3 pi over 2, and that pattern continues infinitely in both directions. I want this specific piece where the point 0, 3 would be. So the x value 0 would lie in between here at negative pi over 2 and pi over 2. So that means that this solution is only good for the domain negative pi over 2 to pi over 2. The now try problem number 15 asks us to solve the initial value problem explicitly. And you might see at the beginning here that we definitely are going to have a vertical asymptote at x equals 0. So first I'm going to rewrite dy dx as, let's see, negative exponent, so I can use the power rule of integration, plus I multiplied both sides by dx to get the differential dy. Integrated both sides, and I have my plus c at the end, so I can plug in 1 for x and 3 for y. Now I solve for c, and I get that c equals negative 11. Well, that will be my solution only for the part where the continuity is. Now I know that there's a vertical asymptote at x equals 0 and the x value is 1. So this solution is only going to work for 0 to infinity. On the left side of that vertical asymptote, negative infinity to 0, this would not work.